Have you ever wondered why the Hamiltonian plays a pivotal role in quantum mechanics, governing the dynamics of particles at the most fundamental level? What makes it so special in the realm of quantum physics? And how does it relate to the Hermitian operator, which is a crucial concept ensuring the preservation of quantum states? Understanding the Hamiltonian and Hermitian operator is not merely an academic exercise. It lies at the very heart of comprehending the behavior of quantum systems. Why are these operators of utmost importance in your learning journey? In this video, we are going to look into these two fundamental concepts. Mastering the Hermitian and Hamiltonian operators empowers you to solve certain fundamental equations and unlock the secrets of a vast array of quantum phenomena. You will also realize that the Hamiltonian and Hermitian operators are more than just mere mathematical entities. They are the gatekeepers in your understanding of the fundamental laws that govern the behavior of atoms, particles, and the entire quantum universe. My name is Shaunak and you are watching this video on my channel Physics for Students. Welcome to this new video unraveling the Hamiltonian-Hermitian connection. Before we go ahead, we first need to understand what is the Hamiltonian, and for that we will delve deep into the life of the visionary William Rowan Hamilton, which is a gateway to understand the genesis of Hamiltonian mechanics. Born in 1805 in Dublin, Ireland, Hamilton was a prodigious mathematician and physicist whose profound insights reshaped the course of mathematical physics. His father was working as a solicitor at Dublin. Through his tireless pursuit of knowledge, Hamilton developed the Hamiltonian mechanics, a groundbreaking formalism that revolutionized classical mechanics and laid the foundation to quantum mechanics. As you can see here, that young Hamilton was capable of doing great calculations at a very fast speed, and in 1827 Hamilton presented a theory of a single function which is known as Hamilton's principal function. He also worked closely, and his career included seminal works in geometrical optics, ideas from the Fourier analysis, and his work on quaternions. Hamilton retained his faculties unimpaired till the last day, and he died on 2nd of September 1865 following a severe and a major attack of the gout. Well, that is basically in brief few points about the great life of William Rowan Hamilton, without which nothing would have been possible. And now we come to the fundamental question, that what is a Hamiltonian? Now, as you can see here, that Hamiltonian is basically, we can call it as a fundamental concept, or what we can call is that it is a kind of a function. It is a mathematical concept, and it rules the world of classical and quantum mechanics. Now, if you see here that it has got the classical physics part and it has also got the quantum physics part. In classical physics, what we can say that it is a mathematical function that describes the kinetic and potential energy. While in quantum mechanics, it acts as an operator governing the time evolution of quantum states. And if you understand this, then predicting the behavior and dynamics of particles in both classical and quantum physics will become easy. So here is a summary. A Hamiltonian is a mathematical function which describes the total energy of a system. So from here, what we can see is that it basically comprises of one concept, that is, it is a mathematical function, and it comprises of total energy. Although we will understand in quantum physics, it is more of an operator, and classical physics, it is more of a function. The question is that, are there any other Hamiltonian functions which are applicable? I'm going to say, is there any way to know that the Hamiltonian functions are only applicable to classical or quantum? Coming up into the next part of our video. So you see, first we dealt with classical Hamiltonians, which is basically used to describe the dynamics of a classical system. They are typically functions which denotes the system's position and momentum, and you know that with Newton's laws of motion, position and momentum are very fundamental in order to predict the behavior of a particle. We also have got quantum Hamiltonians, which is more of a operator, and these operators acts on the wave function of a system. It is no more considered to be a function of position and time. We also got Hamiltonian many-body systems, which is more complex, we can say, is used to describe the dynamics of many interacting particles. Obviously, it would be more complex than the single particle systems. So Hamiltonians for open systems refers to used to describe the interaction of environment and how the other areas surrounding that system actually dictates the rule of the Hamiltonian. So we saw classical, which is more of a function. I would say that it is basically, it is typically function of the position momentum. This is more of an operator. Hamiltonian body many system, it is basically an interaction of particles with complex system, and in dynamical system, it deals with the energy with the system and its surrounding environment. Now the question is that we have understood overall what is a Hamiltonian, although we have not gone into the mathematics, which we will do. But the question is that why do we at all need a Hamiltonian? Could life would have been easy with Hamiltonian, without Hamiltonian, or life would have been difficult? Coming up into the next part of our video. So we will start with the classical Hamiltonians, and the question is that why do we need Hamiltonians? In order to understand the limitation of a system, we always go back to its past. That means a predecessor, a step back. And here we go back to Sir Isaac Newton, and in case of a body considered which is moving in a simple one-dimensional direction, we all know that this equation is quite revolutionary enough in order to define the position, momentum, acceleration, even on a celestial level, the bodies, the sun, planets, and big bodies which are moving and orbiting around a gravitating body. So we can say that this equation, or the further derivation of acceleration as a second derivative of time, etc., are quite good enough with Cartesian coordinates. This is already known and established. But the problem starts from here, when we get into curvilinear coordinates, or when we get into many such bodies which are interacting with each other. So you see more complicated systems, or large number of bodies, or a Cartesian coordinates moving to curvilinear coordinates, or coordinates which are more general, F equals to ma, does not really work out. So the question is that if we are not getting sufficient enough mathematical calculations, or maybe we are getting, but if we use classical Newton's mechanics, it is far more difficult to solve. So the question rises is that where do we find the solution? And the answer is given by this French mathematician Joseph Louis Lagrange. Now this is basically, we are not dealing with Lagrangian equation, but before we go into Hamiltonian, it is definitely important that we know a little bit about the Lagrangian equation in a very simple manner. So what we know is that the Lagrangian, those who already know, definitely you already know for that, is a more or less a general way of describing motion. That means we are not using Newton's laws of motion, as it causes limitations in case of curvilinear coordinates, or coordinates, or particles which are many more in number. So Lagrangian helps us to generalize Newton's motion, and it helps us to solve problems that are difficult using Newton's laws. So now what we see is that the Lagrangian is given by this equation, where L is the Lagrangian, T is the kinetic energy, and V is basically the potential energy. So as we saw, that it is more generalized way of describing Newton's laws of motion. But if we do the real mathematical calculation, we get this kind of equation. We're not going into the complexities of this equation, but what we can say from here, yes, Lagrangian is definitely a function, and it is a function of the system position coordinates and its time derivatives. That means we won't be using force, acceleration, etc., but more generalized into position coordinates and the time derivatives, so that things become easier. So here at the bottom you can see a kind of a summary that it involves Newton's laws involves position velocities. Lagrangian mechanics uses more generalized coordinates and the time derivatives q, and this function are easier to solve mathematical equations in generalized coordinates or with curvilinear coordinates. Now this is basically what we know about Lagrangian. Now as we are in the process of generalizing things, so from here we go to Isaac Newton, and you can see, so from Isaac Newton we go to Lagrange, and Lagrangian is further, I would say, generalized with Hamilton or Hamiltonian equation. So it is a process of generalization. So to take a quick note is that the entire endeavor of scientific studies and mathematical progress is generalization. Isaac Newton's laws of motion got generalized into Lagrangian, then Lagrangian got into Hamiltonian, then came the relativity. From relativity we went to general relativity, from GR we went into string theory, and so on. So we are in the continuous process of generalizing things so that it is applicable on a vast arena of space-time. It makes it easier to work with other formulation of classical mechanics. So if we consider a particle which is moving in a one-dimensional potential, that is in a one-dimensional way, just to avoid further complications, we get this. This is called the Hamiltonian of the system. Let us quickly decipher what are these equations all about in a very simple language. So this is the generalized momentum. Why generalized momentum? We will come back shortly. This is the total energy of the classical particle. This is the kinetic, and this is the potential energy. And when we tell that it is a total energy, that means it is the kinetic energy plus the potential, which is given by this. So now in general we can say that this is the classical equation of motion. So, and we know that kinetic energy is half mv square. So it is as good as to say that this is equal to p square by 2m. So what I'm trying to make a point is this, that in Hamiltonian mechanics you see that the state of a particle is described by its position and momentum, obviously. The second point is that we use generalized coordinate and momenta and to describe the state of a system. So again we are coming to something more generalizing from Lagrangian to Hamiltonian. And the reason why the kinetic energy is written in terms of momentum in Hamiltonian is because momentum is definitely more fundamental quantity compared to that of velocity. So if we write kinetic energy equal to half mv square, and it is almost similar to writing is as p square by 2m. And why it is written in the kinetic energy in momentum? Because momentum is more fundamental than velocity in Hamiltonian mechanics. So this is I would say a kind of an understanding of the equation of the Hamiltonian. Let us now quickly clean up the mess and see what actually it shows. So H is representing the total energy of the classical particle, which is the kinetic plus potential. P is a generalized momentum. Now you can got your answer that why momentum is written, because it's more fundamental. P square by 2m represents the kinetic energy. This is the potential, and you see this one is actually the particle's kinetic energy, which depends on the momentum and the mass, that is m. So this square, p square by 2m, is basically the kinetic energy. Added with that, Vx is basically the potential energy, and we know the total energy of a system is kinetic plus potential, so it adds up to the same way. So now you see the beauty of deriving it from the classical Newton's law. We are sticking back to the same old concept that total energy is kinetic plus potential, but because kinetic and potential, we are writing this in terms of momentum, because momentum is much more fundamental. It looks like this. Okay. So now we come, what are basically the advantages of using Hamiltonian? Obviously we understood that it is more generalized. We understood it is written in terms of momentum. We also understood that it is a I would say coincides manner to write Newton's law of motion in terms of kinetic and potential energy. But what are the uses, what are the advantages of using Hamiltonian? So you see, the first thing is that it is a scalar function. So what does that mean? Which means that it is independent of the direction of motion. Would it have been vector, which I will just show you. Vectors are carrying the magnitude, direction, and even if we form it in tensors, then magnitude, direction, and the plane on which the force is occurring, things become more complicated when we are dealing with multiple particles. So number one, it is a scalar function, which means it is independent of the direction of motion. Number two, Hamiltonian can be derived in a very elegant way. What do I mean by elegant way? In a simple way, in an easy manner, not going into mathematical complication. So here is a chart which gives you an understanding, and Hamiltonian is definitely conserved in many physical systems. Here you see type of function. Hamiltonian is a scalar, Lagrangian is a scalar, but Newtonian is a vector. In terms of conservation, Hamiltonian is conserved in many ways. Lagrangian is not conserved. Newtonian is again not conserved. Again, deriving equations, Hamiltonian is much more easier, right? And Lagrangian is more difficult, and Newtonian is far more difficult because of their natures being vector. So here comes the answer that what is the advantage. First, it is a scalar function, so no more direction or magnitude, only in the direction, easier to solve. Conservation is here the Hamiltonian, the system is conserved, which is not in certain cases of Newtonian Lagrangian, and derivation is much more easier. And why it is easier? It is simple, that it is scalar quantity, and in Lagrangian and Newtonian it is difficult. All this taken together, we understand the advantages, we understand that it's easier, but how do we use the Hamiltonian now in quantum physics, which is another way of using the Hamiltonian, coming up into the next part of our video. Using Hamiltonian in quantum mechanics. So here comes the classical physics part, and total energy obviously will be kinetic plus potential, and quantum physics also the total energy will be kinetic plus potential, and it is denoted by this one, h hat or h. So what we can see from here, before we going into that, I would like to take a pause and tell you that Hamiltonian equation for a single particle, obviously we saw in classical mechanics, is of paramount importance, as it provides a concise and elegant way to describe particles' motion. So we just saw that by combining the particle's kinetic and potential energy into a single function, Hamiltonian simplifies the equations of motion and makes it more manageable to solve. It also reveals the deep connection between energy conservation and symmetries in the system. Now, having said this, the same goes with quantum physics. So you see h equals to t plus v, and it is the same way we just write it. We just write it as this: h bar equals to, h hat equals to t hat plus v hat. Simple. The function which is used as a function of position and momentum is now being replaced as a function of the quantum operators. So if I take this classical equation of one-dimensional body which is moving, this is the Hamiltonian, and if I would say generalize it, you see how it looks. H underscore operator means it is an operator. I'm not mentioning h hat or h just to make it very generalized. So now you see this one is the what? This is the Hamiltonian, this is the Hamiltonian. This is the kinetic energy, and this partial derivative followed by minus. Okay, I will come to what is minus h bar, that is a reduced Planck's constant. I will tell you why it is minus in a few minutes time. But this is the kinetic energy, this is the kinetic energy. Vx is the potential, here also Vx is the potential. So you see, this is an absolute great elegant derivation from the entire laws of classical mechanics. We are just using the reduced Planck's constant, and we are using two partial derivatives, del squared and del x squared, and rest of the things remains the same. So let us sum up the equation part. So you see this minus which I was talking, this is actually which shows that the Hamiltonian is a Hermitian operator. Enter Hermitian operator. Now we are entering into the relationship, which was the basic idea for this video, that what is basically Hermitian and Hamiltonian operator. So if I take, we will go into the Hermitian operator. Before that, two quick notes, that if I take this kind of a three-dimensional box and there are particles which are bumping around, for example, and we take the Hamiltonian of that particle, then it is this simple: h equals to hx plus hy plus hz. And how do we derive this hx? Simple, this one, the partial derivative del squared by del x squared, for y del squared by del y squared, and for z simple del squared by del z squared. And for n particles, this is simple: h equals to Tn, that means kinetic energy of n number of particles plus potential energy of n number of particles. So the negative sign is in front of the reduced Planck constant is introduced in order to show that the Hamiltonian is a Hermitian. And also, in other words, the Hamiltonian operator can be converted into different formulas depending on the functions that is being applied to. So having said this, that how it is being used in quantum physics, now it is the time that we should look into what is the relation between Hamiltonian and Hermitian. We will come back to the postulate number 2, which I just explained in my last video in postulates of quantum mechanics. And the postulate tells this, that every observable in classical mechanics, I hope you understand observable. If you don't, then you can go back to my videos in quantum mechanics. What do we mean by observable? There corresponds a linear Hermitian operator in quantum mechanics. And observable is basically a physical quantity which can be measured in terms of position, momentum, or energy. Now, if I take this kind of a Bohr's atomic model, although this is not relevant today because electrons now are said to exist in terms of cloud, this electron energy, I would say, is associated with a quantum mechanical operator called the Hamiltonian. So as you see, this one I don't need to explain. It is a mathematical function that describes the total energy of the system, and when we measure the wave function of the electron collapses, but it collapses where? It collapses to the eigenvalues of the Hamiltonian that was measured. So here comes the question again, what is the link between Hermitian and Hamiltonian? We saw Hamiltonian is the total energy, that's great. It describes the energy of a physical system, that is also great. But here the postulate says that this is something corresponds to a linear Hermitian operator. What is that? Coming into this part of our video. So this dagger sign is the Hermitian. It's sometimes denoted by dagger sign and other prime, etc. So this was actually designed by the Charles Hermite, the French physicist. And here is the understanding. Hermitian is a general mathematical property which applies to a huge class of operator. This hat is Hamiltonian by William Rowan Hamilton, and this is a specific operator in quantum mechanics encoding the dynamics, especially the time evolution of a system. I have not shown here, but you will see that Hamiltonian of Schrodinger, Hamiltonian of time dependent, Hamiltonian of a time independent Schrodinger equation. There are many such equations which can be easily derived. But here is the point. In quantum mechanics, Hamiltonian is a specific operator. Hermitian is basically a general mathematical property. But out of that, in classical, Hamiltonian is more generic. So just a quick note to those who are watching, don't get confused between the specific operator in quantum mechanics vis-a-vis the general function in classical mechanics. So here is the answer. Not all Hermitian operators are Hamiltonian operators. However, all Hamiltonian operators are obviously Hermitian. The reason is as simple. Hermitian being the general mathematical class, all these things would be under this class of Hermitian. So obviously Hermitians cannot be Hamiltonian, but Hamiltonians, because they are subclass, they will fall under the superclass or the superset Hermitian. So that is why all Hamiltonian operators are Hermitian. So what is a Hermitian operator? There is a typical speciality. That means this is an operator which shows that being equal to its own conjugate transpose, it gives back the original operator. Let us see an example. So here it is. If you take the operator and you make a complex conjugate, it will get back to the original operator. So x equals to x hat. If I do a conjugate operator, see, it gives back the original operator. So the conjugate operator transpose the position, you get the original operator. And the position operator is basically a Hermitian operator. So you see, Hamiltonian operator must be a Hermitian. We just saw that. The question is why? The answer is here. Because the eigenvalues, don't worry about eigenvalue. If you don't understand, I will make a separate video on an eigenvalue. Just consider that, for example, it is just a value. Because the eigenvalues of a Hermitian operator are real numbers. Why real numbers? Because they actually denote different energy levels, and energy levels has to be a real number, physical quantities, and this is the reason. The energy of a particle in a physical quantity that can be measured. So in order to have a physical quantity to be measured, it has to be real, and this real operator is being defined by what? It is defined by Hermitian and Hamiltonian operator, which is basically being transferred to Hermitian operator, taking its own conjugate transpose, has to be a Hermitian. I hope this is quite clear. So this is the thing. The Hamiltonian operator must be an Hermitian operator in order to calculate the energy of a particle. You cannot have the energy of a particle in imaginary other numbers, so that is why it has to be Hermitian. Here is a quick check. If x square is a Hermitian, so we just do the conjugate and we take this, and you see that x square equals to the conjugate transpose equals to x square. So from here we say that x square is a Hermitian. This is I have shown in my earlier video. So here's a quick summary. Eigenvalues of Hamiltonian operators are always Hamiltonian, are always real. The operators of all physically measurable quantities have to have real eigenvalues. The operator itself, in case of a matrix, it can have other complex or imagined numbers, but the eigenvalues must be real. And while a Hamiltonian must be a Hermitian matrix, it can be either real or complex, but remember, the eigenvalues should be real. So what we can tell, that Hermitian operators are a general class of operators that have its own adjoints. Hamiltonian operator is basically used to represent the total energy of a quantum mechanical system. Hamiltonian is a specific operator in quantum mechanics, and the operators of all physically measurables are Hermitians because the eigenvalues of Hamiltonian operators are always real, so these denotes the energy level. So you can take a pause and just take a quick note or take a screenshot of all this, which summarizes the relation between Hamiltonian and Hermitian. Now, if you go back to the postulate number 2 of quantum mechanics, you will understand it better. It says that to every observable in classical mechanics, there corresponds a linear Hermitian operator. Why there is a linear Hermitian operator? Because it has to be conserved, and most importantly, it has to be a real eigenvalue. So now comes the question that can we show that every Hamiltonian is an Hermitian? So let us go back. Here what we saw is that states that every observable in classical mechanics corresponds to the Hermitian operator. So now can we show that every Hamiltonian is an Hermitian? Let us take a quick, very simple example. You see this one, this is a Hermitian operator equal to its conjugate transpose. And if I take that the Hamiltonian operator in quantum mechanics is a Hermitian number, that means the position operator is a hat x equal to x. Now if I conjugate transpose a hat x, it becomes this one, and it again gives back the value of x. So what we can say? We can say that a hat x is a Hermitian operator. So here it is. This is necessary because again the eigenvalues of Hamiltonian operator corresponds to the possible energies of the quantum system. Since energy is always real number, that is why the eigenvalues of the Hamiltonian operator must be a real number. So this actually shows with a very simple one-liner equation that how we can show that by conjugate transpose it gives back the original number. Let us see another quick example. So if I take a one-dimensional box and take the Hamiltonian operator, it looks something like this. I have just shortened it so you can expand it to further equation. This nabla square, this is basically the Laplacian operator. I'm not going to expand Laplacian operator. I hope you know. It is basically the sum of the second derivatives of function with respect to each of its coordinates. Now if I conjugate transpose of the Hamiltonian operator, it gives back this. So the Laplacian operator is a Hermitian operator. So its conjugate transpose is the same as itself. So therefore the conjugate transpose of the Hamiltonian operator is this. And it says this means that a Hamiltonian operator is a Hermitian operator. And you see if I go back here, back to my this one, so here you see that to show that every Hamiltonian is a Hermitian, and we have done with this example, and then we have done with making a Laplacian to show that every Hamiltonian operator is a Hermitian operator. So time to quickly summarize everything, a few more important points between the relation. The first important point is this one, that Hamiltonian operator is a Hermitian operator. They are real numbers, and the eigenfunctions of the Hamiltonian operators are orthogonal. That means perpendicular to each other. Hamiltonian operator is described to see the total energy of a system. The eigenvalues of the Hamiltonian operator are the possible energy levels of the system, and the eigenvalues of Hamiltonian operator, eigenfunctions of the Hamiltonian operator are the wave function that describes the energy. So this one, in terms of classical, you will see it is the total energy of a system. So the Hamiltonian operator's eigenvalues is the possible energy levels, and the eigenfunctions are the wave functions. Next is this, the fact that Hamiltonian operator is Hermitian is important because it ensures energy level. It's a kind of a repetition. And the fact that Hamiltonian operator is Hermitian also ensures that the eigenfunctions are orthogonal to each other. This means that it allows to calculate the probabilities of finding the systems in different levels. I mean to say that is why it is orthogonal. So that's all for today's video. I have given you a thorough idea about the relation between Hamiltonian and Hermitian, which sometimes considered to be very confusing because these two terms are used interchangeably. I thank you very much for watching my videos. If you like this video, please do subscribe to my channel Physics for Students. Click on the bell icon and don't forget to hit a like for this particular video. You can contact me at this email ID, and I have also a channel which is dedicated to Einstein's general theory of relativity. You can follow me on my Facebook, LinkedIn, Instagram and Twitter. And here is a page where I keep on updating beautiful stuffs and biographies and discoveries and a lot more about science, physics and everything. a fan page which is dedicated to the famous British cosmologist Stephen Hawking. You can follow this on the Facebook page. Thank you very much. Physics for Students will continue placing this kind of creating videos, and I hope you liked it. Please mention your comments and what do you think about this video, and wait until I will be back soon with yet another interesting videos. Till then, goodbye.